Let's try to understand the concept of closure of an attribute set X. This concept is very useful in finding the key of a relation given a set of functional dependencies. So the algorithm is given here to determine closure of an attribute set X under a set of functional dependency F. So let us quickly take an example and illustrate how this algorithm really works. So let's assume we have a set of functional dependencies. ESSN functionally determines ename. Project number functionally determines project name and project location. And ESSN project number together determine number of hours for which an employee works. So we know this from our company database. We need to find out closure of an attribute X. So this X can be a single attribute or a set of attributes. Normally, we refer to the left-hand side of each of these functional dependencies. So all of these are of the form X arrow Y. So we need to find out the closure of X denoted by X plus. So look at this algorithm here. Uh, Initially, it assumes that X itself is the closure. So let's consider X as ESSN. So if you go to the first step here, step number 1, X plus is X itself, that is ESSN. So if you enter this loop here, we need another variable old X plus, which stores X plus, namely ESSN. So this is required to set a terminating condition. Otherwise, this repeat until will go on indefinitely. Now, what do we do next? For each functional dependency of the form y arrow z in F, we do the following. So we have to consider each of these functional dependencies are of the form y arrow z. It means now y will be ESSN and z will be the ename for the first functional dependency here. There is a second functional dependency wherein y is project number and z is pname and plocation. And there's a third functional dependency which is x is ESSN p number together and z is your hours. Look at this algorithm here for each functional dependency y or z in F. So this is our set of functional dependencies F, which contains three functional dependencies, each of the form y arrow set. Now, what do we do next? We have to check if x plus contains y. It means whatever is the y in the functional dependency. So let's consider the first functional dependency, which is of the form y arrow z, where y is ESSN and z is ename. So we see that ESSN is contained in x plus because x plus is equal to ESSN and this very much contains y, which is ESSN. So in that case, what do? We update the x plus by including the z part of the functional dependency, which is ename. So x plus initial value is ESSN union the z part, which is ename from the first functional dependency. So the next x plus will become ESSN comma ename. So as you can see, we have found a new value of x plus now. Earlier it was only ESSN, now it has become ESSN comma ename. We have to repeat it until x plus is equal to old x plus. So x plus initially we stored it as ESSN. Now the x plus has changed, so x plus is not equal to old x. So we'll go back in the loop and update old x plus. So old x plus will become ESSN comma ename. So now again when you loop back, take the next functional dependency, project number. Project number is not contained. Now the next functional dependency is y arrow z, where y is p number and z is p name and p location. So if you look at this y is not contained in x plus. So in that case, it doesn't affect this anymore. Similarly, if you take the third functional dependency, ESSN and P number, though ESSN alone is present, but P number is not present. So Y, which is ESSN comma P number, Y is not contained in X. So X plus rather. So this is not true. So in that case, this will not affect the X plus. So X plus will remain ESSN comma ename. Now both have become equal and we come out of the loop. So the X plus or the closure of X for ESSN. So our X was ESSN and its closure, which is denoted as ESSN plus, is equal to ESSN comma ename. Okay, so we have found out closure for ESSN. So similarly, we can find out closure for P number. So let us take X is equal to P number now. Now X plus initially is X itself, so P number. If you consider the first functional dependency, which is ESSN arrow ename, ESSN is not contained in this, so it doesn't affect X plus, it will remain X plus. If you go to the next functional dependency, P number is equal to P name, comma P location. I hope I have taken P location also. Yeah, the second functional dependency. In this case, P number is part of X plus, so X plus need to be updated to P number, comma P name, comma P location. So your entire Z has to be included in X plus. Okay. If you take the third functional dependency, though P number is present, ESSN is not present. So X, that Y is not part of X plus, so no change happens. So the closure of P number will be just P number, comma P name, comma P location. Now if you consider the third one, that is what is the closure of the set ESSN, comma P number. If you take the first functional dependency y arrow z, which is ESSN equal to ename, you will see that ESSN is present here. So X plus will become, initial X plus is this, so X plus will become ESSN, comma P number, comma ename. Similarly, if you consider the second functional dependency, which is P number equal to P name and P location, P number is present here, so X plus gets updated to ESSN, comma P number, comma ename. Now everything which is there in the Z part, which is P name, comma P location, will become part of the X plus. Now the third functional dependency, which is ESSN, comma P number, which is also part of X plus, and its Y Z part is ours, so that will also be included. So ESSN, comma P number, comma ename, comma P name, comma P location, comma hours. So as you can see, the X plus for ESSN P number is all the attributes of all the functional dependencies. So this is the X plus computation, right? So calculating the closure of a attribute set is straightforward. You have to carefully apply each of the y arrow z functional dependency while calculating the closure of an attribute set x or an attribute x. Okay. Now, where do you think this closure concept will be useful? So many a times in the exam they will give a problem. They will give a universal relation R containing some set of attributes, and they will give a set of functional dependencies like f1, f2, fk, and they will not give the primary key of the relation. You have to find out the primary key and then find out whether the relation is in second normal form or third normal form or in BCNF. So to find out in which normal form it is, we require the primary key or the candidate key. If it is given, well, you can proceed immediately. Otherwise, if it is not given, you may have to find it out using the algorithm which is given here. So let's look at this algorithm here, which uses the concept of closure of an attribute X. Okay, so let me take one example here. Let us assume that your R has the following attributes A, comma B, comma C, comma D, comma E. And we are given a set of functional dependencies like F equal to AB arrow C, then BC arrow D, and D arrow E. Okay, and we don't know this relation is in certain normal form or not, like 2NF or 3NF or BCNF. For all of these, we require the key of the relation. Now, is it possible to find out the key of a relation given a set of functional dependencies like this? And the answer to this question is yes. Look at this algorithm here. The input to this algorithm is a relation R and a set of functional dependencies F. Okay, so this algorithm begins by assuming that the key of this relation R is R itself. It means your key is A, B, C, D, E. It means all the attributes of the relation form the key. Normally, this will not be true. We have to eliminate some of these attributes which are not part of the key. Now, how do I eliminate is what is given in the algorithm. So what this algorithm says is that step number 2, for each attribute A in K. Now, K is containing 5 attributes here. Each one of them is designated as A. So don't take this A as A here, just A is any attribute. So now what you have to do is for each attribute A in K, you have to find out K minus A and its closure. Okay, so let us take first attribute A is A itself. That is the first attribute is A here. So K is all of this A, B, C, D, E, and if I subtract A, so what I get is A, B, C, D, E minus A, which is nothing but B, C, D, E, because I have removed A from here. Now we have to find out the closure of B, C, D, E using the functional dependency which are given here. Now look at this functional dependency. You remember the closure algorithm that AB, if it is present here, now you see that B is present but A is not present, so I cannot include C in this. Similarly, BC is present here, D is on the right hand side, it is already part of it, so no need to include. D is here and E is the right hand side, D is present, so I have already included E here. So this will not change, so it will become BCDE. So BCD plus will become ZBCD only. Now what the algorithm says is if K minus A plus, which is K minus A plus is BCDE, contains all the attributes in R. Now all attributes in R are A, B, C, D, E. So does it contain all the attributes in R? No, because A is not present here. In that case, then closure of K minus A plus is BCDE, it doesn't contain all the attributes of R. So in that case, you cannot remove A from R. So the key remains uh, equal to A, B, C, D, E. It means A is an essential part of the key. Okay, so let's see what happens if I try to remove B from here. So next attribute to remove is B. So what you get is A, C, D, E. Okay, now if you apply the functional dependencies, AB arrow C doesn't bring in B. BC cannot be applied because B is not present here. D is there, but D has already included E. So this will be the K minus B plus. Okay, so ACDE will not contain all the attributes in R. So in that case, we cannot do away with B. So key will remain as A, B, C, D, E. It means AB is an essential part of the key. Let us look at C now. So K minus C will be ABDE. Now if I apply AB arrow C, I can restore C. So if I apply AB arrow C, AB is present in this, so this is like your Y arrow Z. So Y is contained in your K minus C plus. So we can include Z into this. So in that case, it will become A, B, C, D, E. And you see that the K minus C plus contains all the attributes of R, and hence you can remove C from here. So that is what the new key will now be, A, B, D, E. Now go and find out K minus D, which is A, B, E. Okay. Now the first functional dependency is AB arrow C. So AB will restore. Now if you try to find out K plus of this, AB will restore C into this, because Y, which is AB, part of X plus, so Z part of that is C, should be included here. Okay. Now if I go to BC, BC is present here, so BC arrow D will restore D into this. Okay, and now D is included, D arrow E, so E is already there. So now as you can see, K minus D plus will get back all the attribute of R, and hence your D is also not essential part of the key. Okay, so the new key becomes your ABE. Okay, it was ABDE, you have to subtract D from here because D is not essential part of this. Now next thing is K minus E, which is AB now. Now you can see that AB is functional dependency is present, so it will restore C. Okay, once you have BC, it will restore. If you look back into the functional BC arrow D, BC will restore D. So the next will become union D. So it will become A, B, C, D. And since D is present, it will give rise to E. So A, B, C, D, E. So you see that all the attributes of R are restored even if I remove E from here. So E is also not an essential part of the key. So what we are left with, the final is AB only. So AB is the key of the relation. Okay, so you can treat this as primary key of the relation. Okay, so what we saw today is two concepts. First one is closure of an attribute X denoted as X plus. So given a set of functional dependencies, we can always find closure of X. Next, how do you find the key of a relation given a relation R and a set of functional dependencies? So the procedure is slightly involved, but if you practice, it will become automatic with you and you will be able to find out key of a given relation given a set of functional dependencies. Hope the video was useful and thank you very much for watching.